nice to see that there are still online seminars ongoing, so that yeah, many mathematicians from around the world can meet and yeah, share on our own mathematical interests. So that's very nice. So thank you for the invitation. So yes, as announced, so the title of my talk is maybe is this is the blue visible, or should I make the I think I can make the, is that better? Maybe
I think so. It's better. Yeah.
it's better. Yes, sorry. Just
Thank you.
I realized maybe you can't see. So yeah. So the title of my talk is the Calabi-Yau Auslander-Iyama Correspondence, and this is based on joint work with Fernando Muro. It's essentially a, a pair of companion papers. One of them is called Obstruction Theory for Infinity by Modules, and it's already in the archive. This is some technical part of this work, and the other one is more or less in final draft, going through last corrections, and hopefully soon will appear in the archive. So in previous work with Fernando Muro, we established a derived version of the Auslander-Iyama correspondence, and this work is a sort of refinement of this correspondence to the Calabi-Yau setting. So let me begin by reminding you what is this derived Auslander-Iyama correspondence. So throughout, we work over a perfect field due to some technical reasons having to do with working with bimodules. So but never mind this assumption, just some mild technical assumption that is needed for most of our results. And we fix a positive integer d. Now, the following theorem is due to Fernando Muro in the case d equals to 1 and to the both of us in general, and it says the following. There is a bijective correspondence between quasi-isomorphism classes of differential graded algebras, let's say A, such that the zero cohomology, that is always an ordinary algebra, is in fact finite dimensional and for simplicity also basic. And in addition, we assume that the rank 1 free digimodule given by the digi algebra itself, that is always an object of its compact or perfect derived category, is what it's called a DZ cluster tilting object in the sense of Iyama Yoshino, and maybe in the periodic case together with, motivated by work of Geiskeller and Opperman. So as a reminder, A is cluster tilting if its additive closure in the compact derived category is, on the one hand, the full subcategory of all objects X that are not extended by A in degrees strictly between 0 and D. And at the same time, the additive closure of A needs to agree with the full subcategory of the compact derived category of A, consisting of all objects Y, not extending A in all degrees that are in between, strictly between 0 and D. And in addition, the Z and DZ requires us to have an isomorphism in the derived category between A and its default shift. So these cluster tilting objects are a distinguished kind of generator of a nice triangulated category, in this case necessarily algebraic, for it is the derived category or the compact derived category of a differential graded algebra. So that's the first class of objects. So roughly speaking, you should think of derived endomorphism algebras of these cluster tilting objects in home finite idempotent complete triangulated categories that are algebraic over, and they are defined over perfect. Okay, that's the first class of objects. The second class of objects is somehow more elementary. These are equivalence classes of pairs, lambda comma I, where lambda is a basic self-injective algebra, and I is an invertible lambda bimodule, so invertible with respect to the tensor product over lambda. So In other words, the tensor product with this bimodule is an autoequivalence of the category, for example, of projective and therefore of all lambda modules. Sorry, it's an invertible bimodule that is isomorphic in the stable category of lambda bimodules to the d plus second CCG of lambda, the diagonal bimodule, so as a bimodule over itself. Now, in this case, due to the basic assumption, one knows that there exists an algebra automorphism of lambda, let's call it sigma, such that I is isomorphic to the twisted bimodule given by the diagonal bimodule with the usual action on the left and the action twisted by the automorphism sigma on the right. And in this case, we can then rephrase this condition as requiring the existence of an isomorphism in the stable category of bimodule between this twisted bimodule and this d plus second CCG of the diagonal bimodule. Now, such algebras are said to be twisted because of the automorphism, d plus 2 periodic because of this isomorphism, with respect to sigma when we want to emphasize which isomorphism is witnessing this property of the finite dimensional, algebra lambda. Now the correspondence between 1 and 2 is given by sending a DG algebra satisfying these two conditions here to the pair given by its zeroth cohomology, that is a basic finite dimensional algebra by assumption, by work of Geiskeler and Oppermann. It happens to be self-injective, so condition A is satisfied, and a small calculation shows that this bimodule over this algebra, so the H minus d cohomology of this algebra is invertible, having to do with this existence of this automorphism. So remember that. So here I have the cohomology of A, and of course, every homogeneous component of this graded algebra is a bimodule over the degree 0 part. So that's how I see this bimodule as a bimodule over H0 of A. So the idea of this theorem is that there is a classification, or if you wish, parametrization of the derived endomorphism algebras of these cluster tilting objects in algebraic triangulated categories that are, I will not repeat this all the time, but home finite and idempotent complete, that is given in terms of a very small amount of algebraic data. Namely, basically you need to remember the zeroth cohomology and the minus d cohomology as a bimodule over the zeroth cohomology. Okay? Now, I also remind you, maybe this is for some of you useful, that the ith cohomology of A is isomorphic to the home in the derived category of A from A to A shifted by I. So in other words, this bimodule here is isomorphic to the home from A to A shifted by minus D. So you can see that by recording this bimodule, in some sense, we are recording at least part of the action of the minus D suspension in the derived category, at least its action on the additive closure of A. Yeah, so we record an algebra that uniquely determines this additive closure, because this additive closure is the same as equivalent to the projective modules over lambda, where lambda is this cohomology, plus certain autoequivalence given by the tensor product with this invertible bimodule corresponding to the minus D shift. Okay? So yeah, so that's it. That's the what we call the derived Auslander-Iyama correspondence. And the purpose of today's talk is to explain a certain refinement of this statement. But before that, let me make some further observations. So if I have a DG algebra as in one, so the derived endomorphism algebra of a DZ cluster tilting object, well, first of all, by the DZ cluster tilting property, its cohomology is concentrated in degrees that are multiples of D. So we call these algebras these graded algebras, these pars. So the degrees are concentrated in multiples, the non-zero degrees. Sorry. Now, the idea from going to 1 to 2 is closely related to the following. So if I take lambda to be the zeroth cohomology of A and I fix an isomorphism in the derived category in A at its default shift, which is part of the requirements of being a decent cluster tilting object, then essentially by conjugation, I can construct an algebra automorphism of lambda, this zeroth cohomology of A, such that I can express in a very convenient way the whole cohomology of A as a graded algebra as essentially a twisted Laurent polynomial algebra. So the idea is that then I can collect all the twisted bimodules, which for just some convenience, the action is now twisted on the left, but of course I can always pass from left to right by taking inverses. So I can take all these twisted bimodules, twisted by powers of this fixed automorphism, concentrated in multiples, so in degrees that are multiples of D, with a suitable, multiplication law, which is reminiscent of the composition law in the graded category associated to the triangulated category given by the derived category of A. So in other words, by remembering lambda and this automorphism sigma, which is essentially equivalent to the invertible bimodule I can completely reconstruct the cohomology of A as a graded algebra. Yeah, so this is what is written here. So this is already some evidence that, so this correspondence is bijective, so it needs to be injective and surjective. Yeah. So for surjectivity, I should be able to reconstruct A from the pair consisting of zeros cohomology and S minus D cohomology, and at least I'm saying, well, I can reconstruct the whole cohomology at least. Maybe not A yet, but at least the cohomology can be reconstructed already from this data. So it's some evidence for the validity of that correspondence. Now, this is maybe some notation and something that will come up later. So if I have a pair lambda comma I given by my finite dimensional basic self-injective algebra lambda and my invertible bimodule I, that I can rewrite as a twisted bimodule by some fixed algebra automorphism sigma, then the statement that this twisted bimodule is equivalent to, sorry, isomorphic in the stable module category to this D plus second syzygy of the diagonal bimodule is equivalent to the existence of an exact sequence of lambda bimodules extending lambda by this twisted bimodule with projective middle terms, right? Because this sequence exhibits precisely this bimodule here as the corresponding D plus second syzygy of the diagonal bimodule. So this information will be useful later. Now, some further notation. When we start with a basic self-injective algebra and a sigma, like in this remark, then this graded algebra here, which is also this twisted to one polynomial algebra, will be denoted by boldface lambda, and probably in speech I will just call it the graded lambda or the graded version of lambda. Yeah, so given this input, I immediately have a disparse graded algebra associated. Okay, so some examples where the correspondence is relevant are the following. So if Q is so this is due to Brenner, Butler, and King, I think. Maybe it was also known maybe to Ringel and Scofield, but I think this is maybe some published, published result. If Q is a Dinkin quiver, then its preprojective algebra is twisted 3 periodic, for example. More general result of Dugas shows that if H is a so-called D-hereditary D-representation finite algebra in the sense of Iyama and Opperman, then is D plus 1 perprojective algebra is twisted D plus 2 periodic. Okay. And so this implies this previous result, because for D equals to 1, the one hereditary algebras are just the hereditary algebras, and the one representation finite algebras are just the finite type hereditary algebras. These are, let's say, for algebraic algebras here is given by, and connected given, so connected algebras given by path algebras of Lincoln quivers. Okay. Another interesting example that is is due to Herschen and Iyama, based on work of Keller and Amiot, or relying in such results in a sort of essential way, is the following. So if I have a quiver with potential, whose Jacobian algebra happens to be self-injective, then its Jacobian algebra is twisted 4 periodic. So here are some interesting sources of twisted 4 periodic algebras. But now I selected only these examples because they all have the feature that they arise as the endomorphism algebra of a DZ cluster tilting object in a D Calabi-Yau triangulated category. In this case, it's some kind of Amiot-Guo-Keller so Calabi-Yau cluster category. So it makes sense, just from a purely sort of conceptual perspective, to try to understand, in the context of the derived Auslander-Iyama correspondence, what happens if we impose additional Calabi-Yau conditions in the set. So, and this is the purpose. So this is what I want to explain in this talk. So I'm actually just going to state our main result in our preprint in preparation, and this is as follows. So again, work over a perfect field. We fix a positive integer d, some integer m, and we take n to be d times m, which is of course a multiple of d. So we now want to have a refinement, so a Calabi-Yau version of the Auslander-Iyama correspondence, which is now as follows. So there is a bijective correspondence between quasi-isomorphism classes of DG algebras A such that, and then I keep the same conditions of the original derived Auslander-Iyama correspondence because I want to apply this. But then I will add a new condition C, which means in part 1, I'm now restricting to a subset of the DG algebra, of the quasi-iso classes of DG algebras considered before. And these are, the condition that I will impose is that A is what is called bimodule right n Calabi-Yau. This means that the n-fold shift of A is isomorphic to the dual of the diagonal bimodule in the derived category of DGA bimodules. And in this case, this implies that the perfect derived category of A, or complete derived category of A, is n Calabi-Yau as a triangulated category. So notice that I could have imposed other variants of condition C, for example, this one, or even being n Calabi-Yau as an additive category, which is in fact weaker. So remember that to be n Calabi-Yau as a triangulated category, there is a condition on certain signs that I will try to explain a little bit later. And those two variants will follow easily from the previous correspondence by imposing some simple assumption on part 2. Here is more subtle because we are asking for a quasi-isomorphism between certain DG bimodules. So this is a stronger variant of the more, let's call them, naive Calabi-Yau conditions that one could impose in this context. So having restricted ourselves in one to a subset of the DG algebras in the derived Auslander-Iyama correspondence, namely those that are bimodule right in Calabi-Yau, well, we expect that in condition 2, we will need to impose some additional condition, let's call it also C, that corresponds to the condition C above, right? Which is the extra condition. So just as before, I have equivalence classes of pairs, lambda comma I, where lambda is basic self-injective. And I have an invertible bimodule already written as a twisted bimodule by some algebra automorphism, such that the D plus second CCG of the diagonal is isomorphic in the stable category of lambda bimodules to these twisted bimodules, witnessed by eta, an exact sequence of bimodules of the correct length with projective middle terms. Now, the additional condition that I obtain is that I now require the existence of an isomorphism of graded bimodules between the n-fold shift of the graded version of lambda as a bimodule and the linear dual of, so the graded linear dual of the graded version of lambda as a bimodule. That's the first condition. And here, of course, I see why I needed to put n to be some multiple of d, because, well, if A is the derived endomorphism algebra of a distant closer tilting object, then its cohomology is concentrated in degrees that are multiples of d, and therefore the corresponding graded lambda, which is nothing but the cohomology, is also concentrated in, the dual is also concentrated in degrees that are multiples of d, and therefore I can only shift on this side by degrees that are multiples of d. So that's why that restriction is necessary. And now, well, this is what you would imagine is enough, right? Because you want the correspondence to be given by the same thing. And of course, whenever I have A isomorphic, so A shifted by N isomorphic to the dual of the diagonal in the derived category of bimodules, of course, I have the same thing by passing two commons, right? And these are nothing but the graded lambdas, right? So the graded lambda. So I will get a bimodule right like this. When I write the brackets is because I'm shifting just not thinking of complexes, just to graded objects, to help myself. So yeah, one would expect, okay, this is certainly necessary. This is somehow obvious. And one could think that this is enough. As it turns out, there is another necessary condition that arises. And if we impose this condition, we can prove the theorem. But we don't know if this condition is perhaps always satisfied so that it is redundant. But we need to impose a condition in order to prove the theorem. And this is this condition now in this yellow rectangle. Namely, there is a certain class in the Hochschild cohomology of the graded algebra lambda, which is what we call in this previous paper the universal Massey product of length d plus 2. I will remind you later what this means, but there is a certain class that I can construct from this data, and associated to the automorphism, the graded bimodal isomorphism phi, there is an operator on Hochschild cohomology called the Batalin-Vilkovisky operator. I will also remind you what it means, or what this is. And then there is an additional condition that one can prove needs to be satisfied, namely that this Batalin-Vilkovisky operator evaluated in this universal Massey product of length d plus 2 necessarily vanishes. Okay? So this is the additional condition. And as I said, if we include this condition in the statement, then we can prove that we have this bijective correspondence. But I repeat, as I will try to explain a little bit about this, how this comes about, we don't know whether this condition is perhaps always satisfied or perhaps is not. The problem is that it is very difficult to make an explicit computation. In most interesting cases, we are already coming from a DG algebra satisfying these conditions, so we know that this will be zero, so there is no need to compute it. The difference will be to try to find some interesting twisted periodic algebra such that there is an isomorphism of graded lambda by modulus like this, and then try to compute this and see if it's zero or not. Yeah? But this is not so easy. Hmm? Now here is where I want to make now a little bit of a small remark about signs, which is remember that when one shifts a graded bimodule, the action on one of the sides, depending on your conventions, is twisted by a sign, and also the linear dual involves some signs. Yeah, so this is related to the difference between being Calabi-Yau as a triangulated category or being Calabi-Yau as an additive category. Yeah, whether one keeps track of these signs or not. Okay, so that's the theorem. Okay, so the theorem is yes, one can restrict the derived Auslander-Iyama correspondence to a suitable class of Calabi-Yau DG algebras. In this case, is bimodal right-hand Calabi-Yau ones. And one can explain precisely what is the image on the other side, under the correspondence. Okay? But this is now a bit technical, and I want to tell you about it a little bit what it is. And this will take us maybe a little bit of time. Okay. So maybe this will give you some idea also of some of the new tools that are needed to prove these theorems. Actually, not a trivial consequence of the other theorems. So first one is this obstruction theory for infinity bimodules that I already explained. It's already in the archive. But this other paper that we are in the process of finishing, it's already maybe 91 pages, including the references. So it's not some kind of trivial modification. Well, it's similar to the other approach, but somehow one needs to do a lot of new things. So it's yeah, maybe. Okay, so let us get going. So let A be a DG algebra. Let's put lambda its zeroth cohomology. Let's ask that this is finite dimensional and basic. And let's assume that A is the Z closer tilting object in its perfect derived category. That means in particular, I have a phi, and I have a sigma, an algebra automorphism of lambda, so that I can form this twisted Laurent polynomial algebra, which is the graded version of lambda, which is nothing but the cohomology of A in a specific presentation. Okay, that's a graded algebra. Now, the first thing I want to remind you of is that because this graded version of lambda is the cohomology of a DG algebra, by a well-known theorem of Kadishvili, the so-called homotopy transfer theorem, lambda inherits from the DG algebra a system of operations. So these are, multilinear operations of RTN called Mn induced by A. So they have n inputs and one output, and are of degree 2 minus n. There is one for each number bigger than or equal to 2. So there is a binary multiplication, which uses the algebra multiplication on the cohomology, but there is also a ternary, quaternary, and so on operations of higher arity, such that the pair consisting of this graded algebra lambda and this system of operations is what is called an A infinity algebra. But in fact, this A infinity algebra is what is called minimal, because the unary operation, which is a differential, is 0 because the cohomology of a DGA in general does not admit any canonical differential. So associated to my derived endomorphism algebra of my DZ closer tilting object, I have a minimal A infinity algebra. Moreover, there exists what is called an A infinity quasi-isomorphism between this minimal A infinity algebra structure on the cohomology of A and A itself that induces the identity in cohomology. The upshot of this is that the derived categories of A and of this minimal A infinity algebra, call its minimal model or a minimal model because it's unique up to non-canonical A infinity isomorphism. These two derived categories are equivalent as DG enhanced triangulated categories. Yeah, so even taking care of enhancements. In other words, for the purposes of the problem we're dealing with, and one can even make more precise statements about the homotopy theory of DG algebras and infinite algebras being equivalent in a suitable sense and so on, it means we can replace our original DGA by a minimal A infinity algebra. And we will see why this is useful very soon. So recall that because A is the homomorphism algebra of, well, the rank 1 Dg module in the derived category, which is by assumption that this is closer tilting object, then its cohomology is concentrated in degrees that are multiples of D. This means that whenever n is not of the form 2 plus D times something, the corresponding n-ary operation on cohomology part of the infinity structure of any one you choose is going to be 0 by some simple calculation using the degrees. So that means that the only operations that I have is m2, md plus 2, m2d plus 2, etc. Yeah, so I have always the binary operation, and then possibly I have as a first possible higher operation md plus 2. Okay, so there is already a simplification. So actually, one thing I want to advertise about this is that in principle, it is quite, in general, it's quite difficult to uniquely determine the quasi-isomorphism time of a DG algebra just from its cohomology and very little of additional algebraic data. But we have put ourselves in a context where many things are, so many things become a bit simpler. For example, the kind of operations that can appear, you can really see these are quite restricted. And they are very, also the degree 0 part of this DG algebra is twisted periodic, etc. So there are many things that are inbuilt into our setting, which is in the end what allows us to prove this kind of theorem. So there is something really very special about being this at cluster tilting that allows this to work. Yeah? So in general, it's hard to expect, I think, results of this kind for arbitrary DG algebras, definitely not, but even it's hard to know for which DG algebras one can expect this kind of theorem, I think. Anyway, so let us continue. Let me remind you also of the Hochschild cochain complex of the graded algebra, so the graded version of lambda. This is a bigraded complex whose component of by degree p times q is the space of linear maps from lambda tensor to the p to lambda in degree q. So operations with p inputs and a single output and operations of degree q. This is equipped with a differential called the Hochschild differential, which is by degree 1, 0. And sorry. And we can see now from this definition that the operations that are part of the minimal A infinity structure on the minimal model that we have chosen of A are elements of the Hochschild cochain complex, well, in which in by degree n comma 2 minus n, so the total degree, the sum of these two degrees is 2. This is the way to remember. In particular, that is true for the first possibly non-trivial higher operation in degree d plus 2. Now, an A infinity algebra is defined by an infinite system. So this multiplication satisfying an infinite system of quadratic equations known as the A infinity equations. And in this case, thanks to the minimality, one can show that the Hochschild differential applied to this operation, which as I explained is in the Hochschild cochain complex in by degree d plus 2 minus d, so again the total degree is 2, vanishes. Okay, so that's the first important observation. So I try to erase something, I can't. Okay, that's the first thing. In particular, we obtain a well-defined class in Hochschild cohomology of lambda by degrees, I said, by d plus 2 minus d. That was what we call the universal massive product. And this turns out to be a quasi-isomorphism invariant of the DG algebra. So this is already one advantage of passing from the DG to the minimal A infinity setting, that this passage reveals an invariant of a DG algebra that is not immediately accessible from the DG algebra itself, but it only becomes manifest once we pass to the minimal model. Just give me 1 second that my computer is losing its battery. think this should work, maybe. Yes, that worked. Okay, sorry about that. Yes, so this is already the first important step, is to have passed to the minimal model of the DG algebra to get access to this universal massive. The fact that this is an invariant of the DG algebra is also related to the disparsity condition. Some technical remark about that. Now, using again these A infinity equations for minimal A infinity algebras, one can show that a certain operation called the Gestenhaber square on the cohomology, on this Hochschild cohomology, applied to this universal massive product, vanishes. In characteristic different from 2, the Gestenhaber square is the same as 1/2 of the so-called Gerstenhaber bracket in Hochschild cohomology, which is an operation that may be more familiar. Yeah. So this is a certain class in this by degrees, but it's not totally arbitrary. It needs to satisfy this additional condition, namely its Gestenhaber square vanishes. Okay. Now, further associated to this class is what we call the restricted universal Massey product. This is obtained by taking the inclusion of the degree 0 part of lambda in itself. This is an algebra map. And then we can restrict this class to the Hochschild cohomology of lambda viewed as a graded algebra concentrated in degree 0 with coefficients in the graded lambda as a bimodule over the degree 0 part. An easy computation shows that this is nothing but the bimodule extension space in degree d plus 2 between lambda and the degree minus d part of the graded lambda, which one can see is this bimodule, because the degree minus d part, this would be this one, but these two bimodules are isomorphic. Okay? So we see that the restricted universal massive product gives me an extension of bimodules of the diagonal by this twisted bimodule, which is exactly the kind of type of extension that we had seen before. And it's a non-trivial fact that because I'm coming from a dz cluster tilting object, I can choose not only the first d plus 1 terms in the, here's missing middle terms of this sequence to be projected bimodules, but also the last one, the last middle term. In other words, this restricted universal massive product, so this is what we call the restricted universal massive product, or is restricted, sorry, it's a witness of an isomorphism in the stable category of bimodules between this twisted bimodule and the corresponding CCG of the diagonal bimodule. Yeah. So this goes back to the conditions in the derived Auslander-Iyama correspondence, right? So we see why roughly these conditions are sort of appearing in a different way than maybe the one would see them at least for the first time. Yeah. So summary of this: the restricted universal massive product is a witness of the condition that the d plus second CCG of the diagonal is stably isomorphic to an invertible bimodule. Okay? That's the way to understand this state. Yeah? That's the upshot of all of this, is that we can understand that isomorphism as coming from an invariant of my DGA, namely this restricted universal massive, well, the universal massive product and its restricted version. Okay. Now, one of the theorems that we proved in our previous paper is the following. If we have two DG algebras as above, such that, maybe let me also, I don't know why I forgot basically. So two DG algebras with isomorphic cohomology as graded algebras, and let's assume that A satisfies the conditions of the Auslander-Iyama correspondence, or basic finite dimensional um, and being this closer tilting, then if it is the case that the restricted universal massive products of A and B are the same, then A and B are already quasi-isomorphic. This is related to the injectivity of the correspondence. Okay, this is one of the statements that one is to prove. So let's give you an idea why this restricted universal massive product is important. I have 60 minutes, right? Yes. Okay.
Yeah, yeah.
Oh my God. Yeah. Okay. Let's see if we make it. So this is still some kind of summary of the other, parts of the other paper that are important for what we're doing right now today. Okay. Now, related to the surjectivity of the original correspondence is the fact that is the following. So if I have a twisted D plus 2 periodic algebra with respect to sigma, and I fix a class that witness a stable isomorphism of bimodules of this kind, so something that looks like it could have been the restricted universal massive product of a DG algebra with cohomology, the graded version of lambda with respect to this isomorphism, so the d-sparse version, of course, then we know that up to quasi-isomorphism of DG algebras, there exists a unique DGA whose cohomology is the graded version of lambda and whose restricted universal massive product is this class. So we can realize all these classes as restricted universal massive products. Okay, so this is, as I said, a reminder of what was happening in the proof of the previous correspondence, so the non-Calabi-Yau version, and why. So what was this universal massive product? What's its restricted version, and why it was important to consider it? Yeah. So it is some kind of shadow of the first, possibly non-trivial Higher operation in a minimal model of the DG algebra I started with. And the way you should think about this DG algebra is as the derived endomorphism algebra of a decent cluster. Okay. So hope this was somewhat helpful, because now we want to move on to the Calabi-Yau version. So let me go back for a second. Well, the proof has two obvious parts. I mean, one part is to check that the correspondence is well defined. So meaning that if I have A, B, and C, then I have A, B, and C here. I know that if I have A and B, I have A and B. So it's just about adding C implies C. If this is well defined, the Calabi-Yau correspondence is just a restriction to a subset of the domain of the non-Calabi-Yau one. So it's automatically injective. So the question is whether it is surjective. So the question is how to go from something as in 2 satisfying these conditions to something as in 1. I know that if I have A and B in 2, I can construct a nice DGA like this. So the only thing that I really need to find out how to do is how to guarantee that there exists some isomorphism of bimodules of this form, witnessing the fact that A is bimodule right in Calabi-Yau. That's really the thing that is missing. But this is a non-trivial statement because I'm starting from the existence of an isomorphism of graded bimodules. But I want to lift this to a more structured statement, which is a quasi-isomorphism of DG bimodules. Okay. So continuing with the same ideas as before, we are not going to move from algebras, graded algebras and DG algebras to bimodule, graded bimodule, and DG bimodule. Okay. So I still have my lambda fixed as before, yeah, coming from the cohomology of a DG algebra of endomorphisms of a distant closer tilting object. And what I have now is some d-sparse graded bimodule. So just meaning as a graded bimodule is concentrated in degrees that are multiples of D. For example, you should think of the diagonal bimodule. Yeah, lambda itself was d-sparse, but I use M because this is more general and also it becomes less confusing. because then when it's hard to distinguish between lambda as a bimodule and lambda as an algebra when it's acting over itself. Okay. So in this case, there is another complex called the bimodule complex of M, which is also bigraded, but it's in fixed by degree. It is the sum of certain trigraded things. So remember, in the previous case, for algebras, we use the Hochschild-Cochain complex to understand minimal A-infinity algebra structures on a graded algebra. Now we want to understand minimal A-infinity bimodule structures on a graded bimodule. So the space of tridegree PQR corresponds to k-linear maps of the following form. So I have lambda to the P on the left of M, lambda to the Q on the right of M, and then M as an output. So you can see these are maps that look like acting on the left and on the right by lambda, so like bimodule, right? With output M of some degree, R in this case. And I can have P terms on the left and Q terms on the right, which you can now imagine this has to do with the notion of A-infinity bimodule. That I will not remind you what it means, but it has to do with this kind of operation, basically. Yeah? Should remind you at least of the notion of classical bimodule and a little bit of the one of A-infinity algebra. So then in by degree now n comma r, I fix the r and I take all the compositions of n of the form p plus 1 plus q equal to n. So n is the number of inputs of this operation. But remember, now there is one distinguished input, the input that comes from the bimodule. And now you see why I didn't want to take lambda equal to n, because then it becomes very confused where is the distinguished input. It's going to appear. This also has a nice differential, becomes a complex called the bimodule Cochain complex of M. It's essentially obtained by tensoring M with the Barre resolution of A on both sides. If you are familiar with such things, then you have seen this before for sure. And its cohomology is just the bigraded extension space of M. Yeah, so this is a way to compute the bigraded extension space of M. Now, in our papers, we define a new complex, which we call the bimodule Hochschild complex of the pair lambda comma m. It's not the same as this. This should be called. This is called the bimodule Cochain complex of M. This is the bimodule Hochschild complex of the pair. It has an explicit description. On the one hand, I have the Hochschild Cochain complex of lambda. Here I have this bimodule Cochain complex of M. And as it turns out, this complex is a graded bimodule over the Hochschild complex of lambda. So I can consider a certain map that turns out to be a chain map. It's even a digibimodule given by the difference of the left and the right action of a cochain here on the identity map of M. Yeah, so the identity map lives in basically the home from M to N, right? So this is where P and Q are 0 and R 0. Yeah. And then I take the co-cone, so the inverse shift of the cone of this map. So everything here has an explicit formula. So we obtain an explicit formula for this co-cone, right? This is given. It's a standard mapping co-cone, so it has an explicit formula. It turns out to be what it's called a brace algebra with multiplication. This is coming from the fact that all of this can be expressed in terms of graded operats. And this is basically the brace algebra associated to something called the linear endomorphism operat of the pair lambda comma m. If you're interested in this, this is in the preprint that it's already online on obstruction theory on A-infinity bimodules. And as a consequence of this, the cohomology of this complex is what is called a Gerstenhaber algebra with respect to the total degree. So it's a graded commutative algebra with a compatible shifted graded D algebra structure. Mhm. Okay. Sorry. Now, so this is some cochain complex that can be used to control the following. So if I fix a minimal A infinity algebra structure on A, this lives in some parts of the cochain. So in the total degree 2 part of the cochain complex, Hochschild cochain complex of lambda, right? The graded lambda. And here I have, so in this part, I have, ways of lambda to act on M. Mhm. And looking at this cocone, I can now look at these two structures when they are compatible. So when this actually defines a bimodule structure over of M over lambda, an A infinity bimodal structure of M over lambda. So this is the motivation to introduce this cochain complex. Now, the idea is now the following. That we want to do is, suppose you have an isomorphism of graded bimodules between a shift of M and its linear dual. So this is the kind of thing we're after in this Calabi-Yau right-hand Calabi-Yau business, right? So one can construct a diagram that starts from this new bimodule Hochschild complex of the pair lambda comma M to itself that first replaces M by its n-fold shift, then dualizes, and then goes back to M using this isomorphism. The idea, what you should have in mind is that here I have, for example, some distinguished cochains, which are a minimal A infinity structure on this, together with a minimal infinity bimodule structure of this, on this, that is compatible with this algebra. These are cochains that live here, right? Because, this, as a graded object, this is the same as this plus this up to a shift, right? So, and then, well, it's like, but maybe you imagine that if M is a bimodule over A, its shift is also a bimodule over A, and the dual of a bimodule is also a bimodule, so that's this. And if I have an isomorphism of bimodules, I can transport a bimodal structure on one thing to the other. This is what this diagram does. But the whole point here is that every one of these maps can be given in terms of explicit formulas, because every cochain complex here is explicit, everything here is explicit, so the composition here is explicit. This is important so that we can make this Batalin-Vilkovitsky operator appear in the statement of the theorem. Yeah. So then in this part, the story becomes very, very explicit. Okay. And now the idea of this map here, which is a capital Upsilon, is that if I start with a minimal A infinity bimodule structure of M over the graded lambda, which now has also a minimal infinity bimodule structure, then I get a version of the universal massive product called the bimodal universal massive product. So it's a similar thing like so it's a similar invariant like in the case of algebras. And moreover, I can transform this structure to another one using upsilon. Yeah. This structure is again living on the same M, but it's the minimal A infinity bimodal structure corresponding to the dual and then shifted by minus n. That's what this diagram does. So it allows me to associate a corresponding bimodal structure that is the one of the shifted linear dual on M itself. Yeah, by some transport of structure. So I need to shift, dualize, and transport back to M. Because what we are interested is, well, if there is an A infinity isomorphism of bimodules between M and itself, but with the two different A infinity bimodule structures, the one given by upsilon, then by unraveling, what I see is that I also get an A infinity bimodule isomorphism between M and the minus n shift of its linear dual, but then I can shift back to this to get a minimal A infinity bimodule isomorphism, A infinity isomorphism between M shifted by N and its linear dual. Yeah. So this is just some trick to pass from analyzing minimal A infinity bimodal isomorphisms like this to things that are only defined on M, but using sort of different presentations of these structures. Yeah. Okay. So yeah, we're doing well, I think. Now, how to connect this to the problem at hand? Well, in the case where M is the diagonal bimodule, there is a quasi-isomorphism between this bimodule Hochschild cochain complex and the graded or bigraded dual numbers valued here, where epsilon is now a variable of by degree 1, 0. So it's essentially two copies of the Hochschild cochain complex. So this you can think of if you put M equals to lambda, this is giving me two ways to compute the Hochschild cohomology of lambda, and up to quasi-isomorphism, more or less, you can get rid of the delta. Yeah, that's the way you should think about this. So there will be two copies of the same thing. Okay, and this quasi-isomorphism has the property that this sends this difference. So remember, this is the difference of two bimodal universal massive products precisely to this Batalin-Vilkovitsky operator applied to the so this is the bimodal. Let me write here. This is the bimodal universal massive product minus another bimodal universal massive product. So this part is common, so it cancels. And here I have the algebra universal massive product of A. Yeah. So using this proposition, what one can show is that if I started with such a bimodal isomorphism, then what will happen is that this will be 0, but then this also will be 0. This is already means at the cohomological level. Yeah. I will not tell you what this Batalin-Vilkovitsky operator is or what is given by. There is some explicit formula. It is, yeah, maybe I can tell you something a little bit at the end, but the idea is that in order to prove this statement here, it is important to have explicit formulas for this, and for this, and for this. Yeah. So for everything that needs to be compared, it's important to have an explicit formula so that you can, compute and check the formulas and check the answer. Yeah. Okay. But this Batalin-Vilkovitsky operator arises sort of from this computation. So that's why for us it appears. It's a way to translate from this new bimodal Hochschild cochain complex to this is, notice that there is no diagonal, no vertical line. This is the ordinary cochain complex of lambda. Yeah, notice that there is an epsilon here. This has to do with the fact that if this was in degree d plus 2 minus d, this is going to be in this degree plus 1 minus d plus 1 comma 0. Yeah, so because this is homogeneous. Okay, so I have 2 minutes in one page. Let me conclude. So this only shows, I mean, this is some idea of how does one show that the Calabi-Yau Auslander-Iyama correspondence is well defined. So why do we have this condition? Yeah. So as I said, it's a necessary condition. One can compute it. It's implied by the existence of such a quasi-isomorphism. In our setting, we don't know if it's always satisfied. Maybe it can be. It would be nice if it could be removed because the theorem will be simpler. But on the other hand, maybe it is necessary. Maybe to conclude, let me just tell you one thing. In the other paper, we also introduced somehow sort of secondary complex, which called the Massey complex or the Hochschild-Massey complex. And there is a variant of this for bimodules. I'm not going to tell you much more about it, but it is defined in terms of bigraded extension spaces, and the differential is given now by insert the bracket with the bimodal universal massive product. This is very similar to what we did in the other paper. But the idea is that there is another complex that the vanishing of whose cohomology is related to the vanishing of obstructions of existence and uniqueness of minimally infinity bimodal structures. Yeah? Let me just say it like this. I'm not going to say more about it because there is no time. This theorem is explained in the paper that it's already online. So the whole idea is to reduce the problem to an obstruction theoretic problem about existence and uniqueness of, in this case, uniqueness of, well, both existence and uniqueness of minimally infinity bimodal structures. That's what we want to know. That part, it uses completely different techniques. It uses techniques of homotopy theory, in particular. You look at the category of DG operads, model structure, related model categories obtained from this one, mapping spaces in the DG category, and certain spectral sequence that arise where computing towers of mapping spaces in that context. So that part of the proof is sort of a completely different kind, although it's of similar flavor of part of the proof of the other correspondence. In particular, this paper that is already online is very much inspired and uses previous work of Fernando Muro by himself in the case d equals to 1, but it's the variant for bimodules. That's the idea. Okay, yeah. Hopefully this was reasonable. I'm finished. Thank you for your
So, thank you very much for your very nice talk. Thank you. Are there any questions or comments?
So everything was either very clear or very confused.
Yeah. Hi, Gustavo.
Hi.
Thank you very much for your nice presentation. Actually, I have a naive question. If I'm not mistaken, the old correspondence that you already proved in previous paper had some consequences in the uniqueness of enhancements. Yeah.
Yes.
I don't know if this refinement also, or this restriction also has some consequence in that direction.
Well, since we rely on the other correspondence, our enhancements that we get here are still unique. We get the additional information that the enhancements are bimodule right and Calabi-Yau, which is not obvious. So what is obvious is, I was trying to explain this before, but I don't think I did a very good job, is that, for example, instead of condition C, I could impose condition, I think in the paper we call this C double prime, which is that the derived category is, the perfect derived category is N Calabi-Yau as a triangulated category. And there is another condition C prime. No, well, actually, well, sorry, this is, I said that actually wrong, it's good to correct it. Is N Calabi-Yau as an additive category. Now, what it's easy to prove is we can restrict here to the additive closure of A and regard this as a D+2 angulated category using the work of guys Keller-Opperman, or here as an additive category. That's condition C double prime, and that's condition C prime. So what is easy to see is that if you ask for this condition, then on this additive category, you have the Calabi-Yau condition, of course, and then you can sort of just put it here. That's it. That's all the thing you need. Or you can restrict here to the degree 0 part, and this corresponds to the condition C prime. What our result shows is that the unique enhancement that exists of this category is in fact bimodule Calabi-Yau in this sense, which is a bit stronger. And maybe I can make another remark for those of you that maybe know about this. You could ask something, a condition even stronger than this, called maybe C tilde, which is existence of right and Calabi-Yau structure, which is a lift to the dual of the cyclic homology of A of this kind of quasi-isomorphism. And this doesn't come out from our work. So on the one hand, we can refine the condition on, so we can establish a property of the statement, but we cannot yet reach establishing the existence of a structure on the enhancement. Thank you for the question.
Thank you very much. Thank you.
Let me raise this. We don't.
Any more question or comments? Is there no comment question? So if not the case, thank you, Gustavo. Thank you very much for your very nice talk.
Thank you. Thank you for inviting me again.
And Gustavo, please send me the PDF of your slides for putting on the webpage of the seminar. Thank you.
Yes, I'll send it to you now. Hopefully now there are less typos than before. Well, and if there are some typos on, hopefully the paper will be online soon, and the paper should be mostly.
Yeah. You can send me for by email, or maybe later. It's not.
Yeah, I
no
send you
problem.
now the slides. Yeah, by email.
Yeah.
Thank you.
Thank you.